Now this course, as I hope you know because you have chosen the course after all, is all about symmetry in chemistry, right? So everybody knows qualitatively what symmetry is. What we learn here is that symmetry is one way of using mathematics. Symmetry is a beautiful subject, right? Symmetry is all about beauty, and beauty is all about numbers. Whether something is beautiful or not depends on whether it has the correct proportions, right? So that is what we are going to learn here in this course. We are going to learn how to use numbers to figure out many things about molecules. That's why it's a beautiful subject. So this is what we are going to learn roughly. To start with, today we will start itself. We will perform a symmetry classification of molecules and we learn what are symmetry point groups. Symmetry point groups are basically like systematic nomenclature of molecules, right? I had a teacher with whom I had studied something at one point of time. His name was Rupendranath Banerjee. He used to stay in Bhupen Bose Avenue, a street in Calcutta, and his father's name was Ram Banerjee. So his friends did a systematic nomenclature of this person. They started calling him Bhupenpalli Ramrupen. Bhupenpalli stays on Bhupen Bose Avenue. Ram is the father's name and his own name is Rupen. Right, so that is systematic nomenclature. Organic chemists, students of chemistry are all very familiar with IUPAC nomenclature. So we are going to learn a similar kind of nomenclature and we will see many disparate molecules which we don't really think that they are close to each other in terms of chemical properties. They actually belong to the same family as far as symmetry is concerned, and these families will be called the symmetry point groups. I think some of you might already know how to work out symmetry point groups. For them it will be a revision. For those who don't know, we will learn how to do this today. Next, what we will do is this. So when we talk about symmetry, we talk about turning things and reflecting things and then doing an inversion and all that. All that is geometry, right? Now geometry is not good enough for our purpose because you cannot go on drawing pictures all the time. So what we need to do is that we need to translate this geometrical understanding into the language of algebra. And as we see, the way we are going to do this translation is by using matrices. Using matrices, so what we will do is we will write a matrix for every symmetry operation, and this is going to transform these geometrical operations to algebraic quantities, and that is something which will make our job really very simple. So as you will see, first of all, we will determine the family of the molecules, and then we will work out the kundli of the molecules, depending on how they behave in terms of symmetry operations. I think everybody has seen some kundli at some point of time or the other. It is not very easy to read, right? You have very strange symbols. Part of it is perhaps to convince people that it is very difficult. So similarly, our kundlis are also going to look very mysterious. But then, as you will see, it is not very difficult to arrive at those kundlis. We are going to call them character tables, right? But before we can get to character tables, we have to learn what are representations. Basically, once again, like the Bhupenpalli Ramrupen, if you want to describe a person, you have to select a set of properties and you have to define those properties for that person. And that is what we will do for molecules as well. And when we do that, you will see that many different kinds of representation will come out. A representation is essentially a collection of matrices, or as we will see, it will point out to a collection of numbers, right? And then there will be big representations that can be broken down into smaller ones, and there will be representations that cannot be broken down any further. Representations that can be broken down will be called reducible representations, and the representations that cannot be broken further, the fundamental ones, they will be called the irreducible representations. And when we go there, we are going to learn that these irreducible representations behave like unit vectors in orthonormal space. They behave like a set of orthonormal unit vectors, right? And that is where we are going to use group theory. And in group theory in particular, we are going to use a theorem which is called great orthogonality theorem. The great orthogonality theorem is really great because without it we could not have gone any further. We would not have had character tables, we would not have had this particular branch of chemistry at all. Okay. Using weight orthogonality theorem, we'll see how we can work out what are called character tables. How you do it, what they are, and of what use these character tables are. As I told you, character tables are like kundalis of the molecules, right? So, if you are a believer in astrology, you say that the kundali can tell you all about yourself, right? How much marks you will get in this particular course, how tall you will be, how long you will live, and so on and so forth. We will see our character tables, without being superstitious, our character tables can actually tell us about many properties of the molecules. Which bond will be there, which bond will not be there, what will be the property, what will the spectrum look like. We are going to consider at least one spectrum, and so on and so forth. So, before we go there, we will learn to do something else. This is a very useful technique. We will learn to generate what are called symmetry adapted linear combinations. Physical chemists love linear combinations. Here what we will do is we will take linear combinations of things that have the similar kind of symmetry. And once we learn how to generate symmetry adapted linear combinations, then the scope becomes really large. So what you can do after that is that you can venture into something as general as molecular orbital theory. When we say bonding, we generally think quantum mechanics, right? We think of equations and then bracket and all that. What we will do is, we are going to take a different approach towards bonding. Of course, all that quantum mechanics will still be there, but we will try to develop a more pictorial representation of bonding with the help of the SLCs, and we will see that that will be complementary to what you learn in courses like CH425, which for those who are new to the system is really the chemical bonding course of our department, which people study in their 4th year or 1st year, depending on which program you are in. And then we are not going to be content in organic chemistry only. We would like to venture a little further into more complicated systems. We will talk also about inorganic complexes. And essentially, we are going to revisit many things that you already know. You know Jahn-Taylor distortion, right? You know about crystal field theory. You know about 10DQ, right? You know, perhaps you even know the molecular orbital theory of inorganic complexes, isn't it? So what we'll do is, we'll just take a little more informed approach to the same problem. I think everybody knows that in an octahedral field, the d orbitals split into the T2G and EG sets. So here we are going to learn why this is called T2G, why that is called EG, and how symmetry has a role to play here. And the whole premise of this is that, you know, symmetry and degeneracy go hand in hand. I was thinking of a particle in a box, two-dimensional particle in a box, right? Think of a two-dimensional particle in a box. Let us start with a square box, okay? And let us think of the 1, 2 and 2, 1 levels. Square box, this side is A, that side is B. Quantum number for this side is 1 and that side is 2. This is one case. The other case is quantum number for that side is 1, this side is 2. Do they have same energy or different energies if it's a square box? So I don't even remember that 8 and all. All I remember is n square by L square dependence, right? N square by L square. So if L on this side is equal to L on that side, then what will happen? 1 by L square will be common, it will come outside the bracket and we will be left with n1 square plus n2 square. Now it doesn't matter whether it is n1 square plus n2 square or whether it is n2 square plus n1 square, they are one and the same. Okay. Now think of a rectangular box. Rectangular box is a little less symmetric than square box. Now what will happen? L1 is not equal to L2. So now see, n1 by L1 square plus n2 by L2 square and n2 by L1 square plus n1 by L2 square are not one and the same. Will you agree with me on that? Right? Which one will be more, which one will be less? Depends on what? On L1 and L2. Right? Which one is longer, L1 or L2? Okay. So see, this is a very simple example where a more symmetric system is degenerate and a less symmetric system is non-degenerate. Symmetry and degeneracy go hand in hand. Now, if I may come to the example that you wanted to talk about, well, maybe one step simpler than that. Think of a free metal ion. A free metal ion has infinite number of elements of symmetry, infinite number of symmetry operations, right? Because it's a sphere, the perfect shape, right? What happens there is that the d orbitals are all degenerate. Now, when I place this spherical metal ion in even an octahedral field, which is actually very highly symmetric, it is still in a less symmetric environment compared to what it was in absence of the field, right? So, what happens? There is a splitting of d orbitals. Why has that happened? Because you have gone down on symmetry. Even the perfect octahedral complex, forget about the antilateral distortion, perfect octahedral complex is less symmetric than the bare metal ion. That is why not all the d orbitals have the same symmetry. They split into two sets, T2g and dg. Okay, right. And then if time permits and if students permit, then we are going to talk about molecular vibrations. I am not very inclined to get into this because molecular vibrations, I believe, are covered in significant detail in CH442, the molecular spectroscopy course, right? So, if we discuss it here, then there will be some redundancy. So, we will definitely go up to here in organic complexes, but molecular vibrations, if time and clientele permit, then we can go into that, alright. These are the textbooks. We are mainly going to depend on these two. This is, can you read the author's name here?
Albert Cotton.
Yes, F.A. Cotton, F. Albert Cotton. And this, actually the cover of this book, the one that I have does not have this structure. Anyway, this is Carter's textbook. And by the way, I am going to share the slides with you on Moodle, okay. And then we are going to use Bishop's book as well. A little bit of Tinkham, not too much. Tinkham is a significantly higher level, much more mathematical book. And then in any physical chemistry course, no matter what you study, you can always fall back on Atkins for something or the other. So, from time to time, we will also fall back upon Atkins. Atkins actually has good examples. Yeah. So, before we get going, to start with, let me ask a question that everybody I think knows. What is a symmetry element and what is a symmetry operation? Operation is something that you do, very good, right? Now tell me what would be a symmetry operation, right? You do something to a molecule and then it looks the same, indistinguishable, you cannot make out the difference, right? And the word that we use is configuration, right? Indistinguishable configuration. Something that we do to a molecule that leaves it in an indistinguishable configuration, or what I have written is equivalent configuration. Indistinguishable is actually a better word, alright. Now, if you perform, so what is a symmetry element? We have said what is an operation. What is an element?
Geometric entity with respect to which
Yeah. So, a point, a line or a plane with respect to which you bring about the change. Okay. A geometric entity, geometric is better, with respect to which the operation is performed. And this geometric entity of course has to be a point, a line or a plane. And as we perhaps know already, the symmetry operation that we perform with respect to a point is called an inversion. Let us say I have a molecule. Let us take a very easy example. I will take my time drawing this, waiting for the changeover to happen. Okay, let us think of this very simple example drawn very badly, right? Benzene. You start from any point on benzene, start from a carbon atom, go to the center, right, and produce this line to an equal distance on the other side. You reach a carbon atom, right? Instead of carbon atom, if I start from a hydrogen atom, then what happens? Start from here, go to the center, produce the line to an equal distance on the other side, you still get a hydrogen atom, right? Let us start from the middle of a carbon-carbon bond. Go to the center, produce a line to an equal distance on the other side, you reach the middle of a carbon-carbon bond. So start from any point in the molecule, draw a line to the center and then produce a line to an equal distance on the other side, you should get the same thing back. This is called inversion symmetry. Okay. The next thing, of course, is the line. What can you do with respect to a line? This is a line. What do you do with the line? You can rotate, right? So, a line, the operation associated with a line is rotation. And as I think all of us would know, it can be either simple rotation or it can be not so simple rotation. Depending on what it is, you call it either a simple axis of symmetry or alternating, and there is another word, improper axis of symmetry. Proper axis of symmetry, improper axis of symmetry, alternating axis of symmetry. Simple rotation is very simple, as the name would suggest. Let us take something as simple as water, since we want to talk about simple axis of symmetry. Right? Now, if you think of this line, rotate it by how much? Which angle? What angle? 180 degrees. Or 2 pi by 2. Then water looks same once again. What happens if I rotate by 90 degrees? Water that was in plane goes out of plane. So that is not indistinguishable. Right? Alright. So this is a simple axis of symmetry and we call it a C2 axis of symmetry. Where did the 2 come from? So this is from this 2, right? Not this 2, the 2 in the bottom. So if I rotate it by 2 pi by 3, it will be called a C3 axis. Okay. Can you think of a molecule which has a C3 axis? Ammonia. Draw it like this, one bond coming out of the plane, one bond going behind the plane. Where is your C3 axis? This is your C3 axis. This is your C3 axis, right? You rotate by 120 degrees, which is 2 pi by 3. Fine. Now, or you can have a complex rotation, right? What does that mean? You rotate by 2 pi by n, and then you reflect with respect to a plane that is perpendicular to the axis. Any example? Cyclohexane, chair form or boat form? Yeah. What happens? Let me try to draw the cyclohexane in a different way. Okay, because when you talk about symmetry, it is very important to develop a three-dimensional visualization. In fact, we use models for it today. I forgot to bring it, unfortunately. Models are a lot of fun. So let us look down upon the molecule, not in the figurative sense, in the actual sense. Okay, what would you see? You would see, forget the hydrogen atoms for now, you would see these 3 carbon atoms, right? And then far away you would see these 3 carbon atoms, right? And if you just join them by the line, this is what they look like, right? Is that right? Star of David. This is called the Star of David. Right? In the current political scenario, everybody knows the Star of David. Is this correct or not? Can I draw cyclohexane like this? Of course, these are not the bonds. These are just the 3 carbon atoms on the top, I just joined them by some line, and these are 3 carbon atoms at the bottom. I have joined them by dotted line. Okay. Now it's very easy to figure out. Now think of this axis. It's very difficult to figure out from there. Think of this axis, okay, perpendicular. And the way in which I could perhaps draw it is, I'll draw a plus sign. I hope you are familiar with this convention. Plus means it's jutting out of the paper, minus means it's going down from the paper, okay. So now, with respect to this axis, if I perform a C3 rotation, is that big enough for you? The letter is big enough for you? Okay, good. If I perform a C3 rotation, then what will I get? I'll get something like this. Pardon my bad artistic skills. Oh, that is C6. So, if I perform another C3, then what will I get? I get identical or indistinguishable, right? So, where is then, what do we draw now? This is your C3 axis, fine. But will you agree that it's also a C6, S6 axis? Yes. If I went here and then if I reflected it with respect to the plane of the paper, then I would get an indistinguishable configuration, right? Right? So, the C3 axis doubles up as an S6 axis. And why do we bother about alternating axes of symmetry? You have studied this in organic chemistry perhaps? Chirality is associated with presence or absence of, presence or absence. If alternating axis of symmetry is not there, then it is chiral or achiral? Okay. So, that's all about axis. Now, so now we have talked about point, we have talked about line. I am going really very slow here. I am sure I am going too slow for some of you. But then, you know, as the famous song says, it's always good to start at the very beginning. That's a really good way to start. Now, what do you do with respect to a plane? You perform reflection. Reflection is something that we don't even have to define. Everybody knows what reflection is, right? Yeah, that's what it is. Now, some other definitions that we need to remind ourselves are principal axis of symmetry. In a molecule, it is possible that we will have several axes of symmetry. Principal axis of symmetry is the one with the largest value of n. Cn with the largest value of n is called the principal axis of symmetry. Okay. So, if I go back to this example of benzene, what am I doing? What are the axes that you can see? I think you will agree with me if I say that this is a C6 axis of symmetry. In addition to that, do you see some other axis of symmetry? C2, where is C2? Yes. How many such C2s will be there? 3 will be there. Anything else? Very good. So, this is another kind of C2. Right. So, how many total axes of symmetry are there? 3 plus 3 plus 1, 7. Out of which C6 is the principal axis of symmetry. Alright. I keep forgetting when it is 1, when it is 2. Yeah. Now, when you have a principal axis of symmetry, then you can actually classify the planes of symmetry if they are there. A horizontal plane of symmetry is a plane to which the principal axis is perpendicular. Once again, it is easiest to understand with the example of benzene. The molecular plane of benzene is a horizontal axis, right? So, this is the molecular plane, this is your principal axis of symmetry. Principal axis is perpendicular to the molecular plane. So, this plane is called horizontal. So essentially what you are assuming is that the principal axis is always held vertical. Okay. Now, vertical plane is a plane that would contain the principal axis, something like this. If there is a plane like this, that is called a vertical plane. Does benzene have vertical planes? Huh? Similarly, through the carbon atoms, 3 of those, and through the midpoints of the bonds, 3 of those. Right? But in case of benzene, we don't call them vertical planes. There is a special name for those vertical planes. They are called dihedral planes. Dihedral planes are vertical planes which bisects the angle between C2 axes. Remember those C2 axes? Will you agree with me that the planes we are talking about, they bisect the angle between two C2 axes? Right? So, let me just draw it afresh. This is one C2 axis, this is another C2 axis, this is third C2 axis, right? Now think of this plane like this, right? Perpendicular to the plane of the molecule. Doesn't this plane bisect the angle between this C2 axis and this C2 axis? It does, right? So it's, in this case it is called a dihedral plane. Okay. Now, if you know which symmetry elements and which symmetry operations are there in a molecule, then what you could do is, you could develop a systematic nomenclature for that class of molecules using the symmetry operations that are there. And this is something that we should be experts in. I show you a molecule without actually going through all this algorithm, you should be able to tell me which point group it is. So this is a very popular table that nobody uses. You really don't need this table. Okay, it is a nice systematic way of showing it. So what it says is that there are different ways of drawing this algorithm. I got it from this website that is mentioned here. You will find it in any standard book of physical chemistry. Right? So it says that first of all, see whether the symmetry is really very low. C1 would mean what? What is C1? C1 means you rotate by 2 pi. Right? So you rotate anything by 2 pi, you reach not only indistinguishable but identical configuration. Right? You take a porcupine and rotate it. Even the porcupine would have C1 symmetry. So if there is nothing else, you have to give it some name, you cannot leave the poor chap unnamed. So then we call it C1 because C1 axis is always there for everything, not only molecule. Right? Molecule, chair, table, planet, asteroid, anything and everything would have this C1 axis. Okay. And next thing to ask is the other end of the spectrum. If it is not a group of low symmetry, is it a group of very high symmetry? We are going to discuss these groups: tetrahedron, octahedron, icosahedron, C infinity V, D infinity H. We will see what they are. They are special groups. Tetrahedron, icosahedron, octahedron, these have multiple principal axes of symmetry. Okay. And C infinity V and D infinity H are essentially linear molecules. Linear molecules with or without inversion symmetry. If not, then what we do is we look for the highest order rotational axis. What is the principal axis of symmetry? Okay. Then if perpendicular C2 axes are there, then the name will be D. If there is no perpendicular C2 axis, the name will be C or maybe S. Okay. So here this is a little easier. First question to ask is, in addition to the principal axis of symmetry, do you have a horizontal plane, sigma h? If you have a horizontal plane, then what do? You take Cn from the principal axis and you take H from horizontal and you call it CNH. It's not very difficult to figure out actually. If there is no horizontal plane of symmetry, you ask at least, is there some vertical plane of symmetry? So remember, horizontal has higher preference over vertical. Right? We like to sleep rather than stand. So horizontal has higher preference over vertical. So if there is no horizontal plane of symmetry, then look for vertical planes of symmetry. And if vertical plane of symmetry is there, then I think you can guess what the name is going to be. Cn, whatever the value of n is, 2, 3, 4, 5, 25, Cn V. And then even if that is not there, then you ask, so what is it? Is there an alternating axis of symmetry? If there is no alternating axis of symmetry, then you have no option but to call it Cn. See, this is the only part where you actually need the algorithm. This is where people get confused. Otherwise, you can work out intuitively. Here, this is what you really have to remember. If there is no horizontal plane of symmetry, no vertical plane of symmetry, then you ask, is there S2n? Cn is there and is S2n there? For benzene, for example, what is the principal axis of symmetry? C6. Benzene is not a good example actually. What about the chair form of cyclohexane? What is the principal axis of symmetry? C3. Do you have S6? S6 we just showed. S6 is there. So that is the kind of question you ask here. No other plane is there, let us say. That is not true for cyclohexane. But suppose there is no plane of symmetry, no nothing. Then you ask, is there S2n? If S2n is there, then you actually call it S2n. If S2n is not there, then only you call it very reluctantly Cn. Cn is the last option. If the pure molecule has nothing other than a principal axis of symmetry, then only you call it Cn. Otherwise, you try to find some more glamorous name for it. Okay, and you try very hard. You even look for the alternating axis of symmetry. Now, if the answer to this question, is there perpendicular C2 axis is yes, then you don't call it C anymore. Because in addition to principal axis of symmetry, it has some more axis, C2 axis. So even in the name, it should have some more. D is equal to C plus 1. So D is more than C. So instead of C, you call it D. Alright? So you call it D. And once again, you ask the same question that you asked here. You ask, is there sigma H? If sigma H is there, then you don't worry, you just name it DNH. And if sigma H is not there, then you look for sigma D. Remember, it's not going to be sigma V anymore. Right? Because perpendicular C2 axes are there. So, if vertical planes are there and they bisect the angles between the perpendicular C2 axes, then you will call them dihedral plane, not vertical plane anymore. So, if sigma D is there, then you call it DND. And then if sigma D is not there, then once again, with a heavy heart, you call it DN. Alright?